This is Martin Carlisle with James Brahm Returns from pico2018. 2018. Dr. Zernon has finally approved an update to James Brahm's spy terminal. Someone finally told them that ECB isn't secure. Fortunately, CBC mode is safe, right? Connect on port 22666. All right, so we'll go ahead. And I can encrypt a message. It's going to let me enter part of a message and more of a message. And it gives me an encrypted blob. And then I can take one of these encrypted blobs and I can send it, and it'll tell me if it successfully decrypts or not. Oh, here it says I can't reuse IVs. So if I put in a different message, then it'll tell me that it did not decrypt successfully. So basically, when I put in encrypted messages, I'm going to be able to get out one bit of information. Now, what killed SSL3, which is the hint, is a Poodle attack. And the issue with the Poodle attack was that the block cipher had padding at the end, and that padding at the end was not deterministic and not covered by the MAC, which meant if we had a full block of padding at the end, 16 bytes, that last byte would be 16, but the 15 bytes before it would not be deterministic, i.e. their values aren't known, and they're also not checked as part of the message authentication code. So that's going to be what's really key here. So we'll be able to take a block from previous in the message, substitute it as the padding block, and then because this ciphertext is random each time, because the initialization vector is random each time, we should have a 1 in 256 chance of this last byte coming out to be 16. If this last byte comes out to be 16, then we can know that the ciphertext, which is also, let's say, over here, its value with exclusive OR with its previous block, then we exclusive OR in that 16, and we can actually extract 1 byte of plain text from a previous block. We'll then slide the blocks until we manage to extract a lot of text. So I've created a Python program for doing this. And so what I've done here is I've made the prefix, the first part of the situation report, be 43 X's minus however much of the key I figured out so far. And then the second block, and it's nice that it lets me split this message into 2 parts, which is going to allow me to slide one character that I don't know into a particular known spot at each time. So I'll have 51 Y's plus however many I've figured out so far. And then at each point, I'm going to send the message. And here, when I go to decrypt, I'll send everything but that last block of padding, and I'm going to repeat the block containing the 128th character. So this is the 128th character because there's an IV block at the beginning that subtracts 32 from that, and then there's 2 characters of hex for each byte of input. So I'll send that, and then I'll check to see if it was successful. If it was successful, I can exclusive OR that last byte of encrypted text with the 16 with the byte that I've gotten from that last block, and that's going to give me 1 letter of the key. So I'll go through that again. Here we know this value here is going to be 16 if we were correct. So 16 exclusive OR with this byte of the previous ciphertext is equal to this value here, which will be the same as the previous value, which will be a byte we don't know of plain text exclusive ORed with a previous byte. So solving that simple equation, we get 1 byte of plain text. And then if we run that, and I let it run for a very long time, you'll see that it eventually comes up with the key.